Hello everyone, and welcome to this presentation on a key concept in solid mechanics, stress concentration. Stress concentration refers to areas in a material where stress is significantly higher than the surrounding regions, typically caused by abrupt changes in geometry. Common causes include notches, sharp corners, holes, and grooves. These features can cause localized stress spikes that are much higher than the average stress in the material. Understanding this phenomenon is crucial for engineers because it directly affects the strength, durability, and safety of structures. If stress concentration is not addressed during design, it can lead to premature failure, especially under cyclic or dynamic loading. In the image you can see here, we can see the stress concentrations along the X and Y axis in opposite magnitudes with the purple and red. And then in the middle is green, which is closely matching the stress of the surrounding areas. But these are a lot higher and lower in compressive and tensile. To illustrate how critical this concept is, let's look at a well-known historical example, the de Havilland Comet aircraft. The Comet was the first commercial passenger jet introduced in the 1950s. After several tragic in-flight failures, investigations showed that the aircraft had square windows, which caused high stress concentrations at the corners. These localized stresses initiated fatigue cracks in the fuselage, which grew over time and eventually caused the aircraft to break apart in midair. Engineers later redesigned the windows with rounded corners to reduce the stress concentration. This modification significantly improved the structural integrity and became a standard practice in aircraft design. It is a perfect example of how geometry affects stress and safety. We can see a visual representation here of the aircraft's windows. They look awfully square compared to the ones that we have today. From a theoretical standpoint, we quantify stress concentration using the stress concentration factor, often written as K sub T. K sub T is defined as the ratio of the maximum localized stress to the nominal or average stress. This factor is influenced by the shape and size of the discontinuity, the type of load applied, and the material properties. For example, a small hole in a wide plate under tension can produce a KT of 2 to 3, meaning that local stresses is 2 to 3 times greater than the nominal stress. We can see in this graph here that the ratio of the radius of the hole over the distance from the edge of the hole to the edge of the plate, as that ratio decreases, the K sub T increases, which means it has a higher likelihood of failure. Engineers can refer to standardized charts and use handbooks or use computational tools like finite element analysis or FEA, to calculate K sub T for more complex shapes. So how do engineers solve this problem? First, we can modify the geometry, replacing sharp corners with rounded fillets, significantly reducing K sub T. Even small fillets can lower peak stress dramatically. We can also use relief grooves or holes to redirect stress paths and reduce concentrations. Second, material selection is important. Ductile materials can absorb more energy and tolerate higher stress concentrations before failing. Additionally, increasing the thickness or reinforcing critical regions can also help. Finally, simulation tools like FEA allow engineers to visualize stress distribution in a model. This enables them to identify critical areas and make informed design decisions before physical testing. These solutions are widely used in aerospace, automotive, biomedical, and civil engineering applications. We could see a program similar to FEA was used to simulate this solid material, and we can see the radius of the fillet as it increases, it lowers K sub T. And we can see that the stress is less prominent. In summary, stress concentration is a critical concept in solid mechanics and structural design. Ignoring it can lead to serious consequences, while understanding and mitigating it leads to safer and more efficient designs. Real-world disasters like the Comet aircraft failures remind us of the importance of thoughtful design. Engineers today use a mix of theory, experience, and simulation to reduce stress concentration and improve product performance. Whether we're designing bridges, cars, machines, or aircraft, reducing stress concentration is essential for ensuring safety, durability, and success. Thank you for watching my presentation.